Welcome to the next video. In this, we are still in the chapter 2, basic concept of general codes, and we're looking at an introduction to codes and to coding in this chapter. So what is a code? We already saw in the introduction that a code is a device that adds redundancy. And the layman's definition is that an error-correcting code is a device that adds redundant information to a block of data symbols. And we use block codes purely in this lecture. And we use this information to correct or detect potential transmission errors. So the terminology is that the input block contains k bits, and after encoding, we get n larger than k bits. And then we defined the rate of the code already. The rate is given by k over n, so it's the fraction of input bits to output bits. The rate is high, the amount of redundant information that we add is small. If the rate is low, the amount of redundant information that we add is very large. And we're looking at a very, very simple introductory example of a code that has a rate 4 over 7. So we would like to transmit 4 data bits, U1, U2, U3, and U4. And we use a total number of n equals 7 code bits for this. So we have 7 minus 4, 3 parity bits at our disposal to protect the data against transmission errors. So we have parity bits P1, P2, and P3. And we choose the parity bits in the following way. First, we draw 3 circles, circle 1, circle 2, circle 3. Each circle corresponds to a parity bit. And we draw these circles such that they overlap, at least partially. And in the intersections of the circle, we write our information bits. So we write U1 in this intersection of circle 1 and circle 2. We write U2 in the intersection of circle 2 and circle 3. We write U4 in the intersection of circle 1 and circle 3. And we write U3 in the intersection of all 3 circles. So and now we choose the parity bits such that the number of ones in each circle is even. That's called an even parity constraint. So we have 3 circles, and in each circle there's only a single parity bit. So that's something that we can easily do. We can process each circle after each other, and we select the P such that the number of ones in each circle is even. This is essentially the very famous 7-4 Hamming code that Richard Hamming came up with for protecting the data in his electromechanical computing device. So let's do an example. We have a data word U1, U2, U3, U4, which is 1, 0, 1, 0. So we write 1, 0, 1, 0 in this intersection. And then we select the P's such that the number of ones in each circle is even. So we have U1 is equal to 1, U3 is equal to 1, so we have already 2 ones. Then U4 is equal to 0, so we already have an even number of ones, and we select P1 to be equal to 1. Then we're looking at this circle. Again, we see we have U1 and U3, we have an even number of ones, so we can select P2 to be equal to 0. In the third circle, we only have a single one from the information, so we see that we need to set P3 to be equal to 1 in order to have an even number of ones. And we see that we obtain the parity bits by taking the exclusive OR operation of our information bits. So U1 XOR U3 XOR U4 will give us P1. And we saw that the XOR operation corresponds to the addition in our field GF2. So we can abbreviate the XOR by a plus. So P1 is equal to U1 plus U3 plus U4. P2 is equal to U1 plus U2 plus U3, just by looking at the circles. And P3 is equal to U2 plus U3 plus U4. And that allows us to calculate P1, P2, and P3. So we have encoded our first code. And now we are going to look at the transmission over a channel. And we're looking at the transmission over the binary erasure channel as a very simple channel model. And we assume that we lose information during the transmission. So we lose information about the bits U2, U3, and P2. So essentially we have a word that we transmit. So we say we transmit X is equal to U1, U2, U3, U4, P1, P2, and P3, which is equal to 1, 0, 1, 0, 0, 0, 1. And now we receive, after the transmission, we lose U2, U3, so we have question marks in those positions, and we lose P2. And what we do is, for clarity, we denote the parity bits by green numbers so that we can easily recognize them as parity bits. P1, P2, and P3. And we see that we have lost essentially 2 information bits. So we need to recover those. It's also advantages if we can recover the parity bits, but it's not needed that drastically as the information, because the information is what we would like to have. So we'll see a very simple iterative processing algorithm. We saw in the introduction that modern coding is all about simple iterative processing. And the way it works is the following. So this very simple algorithm is very, very, very simple. So we find a circle that has a single question mark, and we recover the missing bit by fulfilling this parity constraint. So we know we want an even number of ones in each circle. If there is one single question mark in the circle, we can easily set this missing question mark because we know that the number of ones must be even. So we just count the number of ones. If it's even, then the question mark must be a 0. If it's odd, the question mark must be a 1 to make an even number of ones. And we just repeat this process until there are no more question marks or no more circles with a single question mark. This is essentially the decoding algorithm that we're going to use for very advanced codes. It's a very simple decoding algorithm, but we're going to use it for very advanced codes. The goal of the lecture is to get an understanding of why this very simple algorithm works, and in designing the codes such that it works with a very high performance. And that's the main idea. We start with something very simple, but we design our coding schemes such that they are matched to this very simple decoder. So let's proceed with this simple algorithm. So we're looking at the first circle, the one on the bottom left. So we see this circle has a single question mark. It's U3. So we can recover the single question mark by looking at the number of ones. We have U1 is equal to 1, U4 is equal to 0, P1 is equal to 0. So we only have a single 1, so U3 must be equal to 1 in order to have 2 ones, an even number. So we can recover U3 is equal to 1. So we have recovered already our first bit. So we have U3 is equal to 1, and now we're looking for a circle with a single question mark. This circle has 2 question marks. We cannot use it. This circle has a single question mark, so we will use it. So it's a single question mark, this guy, and now we can proceed. So we can, looking at this circle, we see we have U3 is equal to 1, U4 is equal to 0. P3 is equal to 1, so we have two 1s, so U2 can only be 0. Otherwise, the constraint wouldn't be fulfilled. So we can set U2 to be equal to 0. That's what we do, looking at this circle, and we can also resolve it mathematically by adding the missing terms, U3 plus U4 plus P3, and this gives us U2 to be equal to 0. So we have recovered U2, and there is a final circle. So this one means we can recover P2. We have U1 is equal to 1, U2 is equal to 0, U3 is equal to 1. We have two 1s, so P2 must naturally be equal to 0. So with this very simple algorithm, we have successfully recovered U1 is equal to 1, U2 is equal to 0, U3 is equal to 1, and U4 is equal to 0. Perfect. That was the very simple introductory example, and that's the very famous Hamming code with a very simple suboptimum decoder. So it's not an optimum decoder, it's a suboptimal decoder for the binary erasure channel. But we'll see that we can design code that work extremely well for this very, very simple decoder. So this was our introductory chapter. In the next one, we're going to look at block codes in particular, and we're going to look at a few block codes and a few bounds on codes in the next chapter.